extremely attentive due to the window problem. Okay, thank you very much for your kind introduction, for the kind invitation to participate at this program and to be at this wonderful place. So the title has been shortened a little bit since I did not see the need to include the abstract already in the title. So in this talk we will be concerned with diffuse interface models for incompressible, immiscible two-phase flow. Two positive features of diffuse interface models are well known. First, their capability to capture topological changes in a natural way, and secondly, conservation of mass is also guaranteed. Not only conservation of mass, but conservation of individual masses. Everything started some 30 years ago with the famous paper of Hohenberg and Halperin, where they introduced their so-called Model H, which coupled a Navier-Stokes equation and a Cahn-Hilliard equation to model two-phase flow of liquids with equal mass densities. And in the sequel, quite satisfactory theory has been established concerning mathematical analysis, concerning numerics, concerning numerical analysis, but only confined to the case of equal mass densities. Surprisingly, the case of different mass densities, which of course is much more natural to consider, turned out to be much more complicated. And even 3 years ago, there was no model at hand which is at the same time consistent with thermodynamics and which allows for numerical treatment. In fact, there was at that time only one model, namely the model by Löwenkrupp and Druskinowski, which was consistent with thermodynamics in the sense that if no external forces are applied, then the energy at a later time can be bounded by the initial energy. So I will start this talk with some remarks concerning modeling. I will introduce a new model which was developed together with my German colleagues Helmut Abels and Harald Garke, and which is the first model which is at the same time consistent with thermodynamics and which allows for a divergence-free velocity field. And using the structure of this model, it is possible to construct a stable numerical scheme. And stable means that the same energy estimate which we want to have in the continuous setting carries over to the discrete setting. So in this sense, this scheme is discretely consistent with thermodynamics. And having the structure at hand, we will be able to prove its convergence to a solution in the continuous setting. And the last part of the talk will be devoted to two questions. So the first question is, does it really work? Can we produce nice pictures? And the second question is, given the fact that there's really a zoo of diffuse interface models, also for the case of different mass densities, what is really the effect of having now this attribute being consistent with thermodynamics? So is it of practical physical significance in the sense that we get different results, or in the sense that we even can identify an experimental setting where a model which is not consistent with thermodynamics becomes unstable? Okay, so that's the plan for this talk. And let me first name my collaborators. So concerning practical numerics, these are my colleagues from Erlangen, Fabian Klingbeil and Stefan Metzger. Concerning modeling, I mentioned already Helmut Abels and Harald Garke from Regensburg. And everything has been supported by the priority program 1506 of German Science Foundation. So before getting medias in res, let us just mention some properties of diffuse interface models. So first, we have a smooth order parameter, the phase field, which is modeled by Cahn-Hilliard equation in the end. Secondly, the interface has a finite width, in contrast to sharp interface models, of course. And we are looking only at a momentum equation for a cross velocity field, so we have to do some kind of velocity averaging. And now here this was indicative, the evolution is energy driven. One also could write the evolution should be energy driven, but in the end it will be energy driven. Okay, so let me now start with the model by Löwenkrupp and Truskinowski. As I said, that's the first model which is consistent with thermodynamics. And you see here a momentum equation. You see the continuity equation. And you see a type of a Cahn-Hilliard equation. And if you count the unknowns, then you realize that the pressure is really an essential unknown in this problem. Now concerning the velocity field V, it is a barycentric velocity, so it has been obtained by mass averaging, so rho 1 and rho 2 to denote the velocities of the individual species involved in this two-phase flow. And the problem with the pressure is, it is an essential unknown in this problem. It appears in the chemical potential, so it is a high order coupling to the Cahn-Hilliard equation, but there is no a priori estimate available. So Helmut Abels has been able to prove by some fancy ideas existence of a solution to this model, but numerically there is just nothing available. Okay, so let us concentrate on this kind of velocity averaging, and let us probably change it in the way it has been done 6 years ago by Ding, Spelt, and Shu. So they introduced cross velocity by volume averaging. So these weight factors phi 1, phi 2 are given as the ratio, as the quotient of the actual mass density divided by the mass density the species would have in a pure phase. And in addition, they require something which can be called volume incompressibility, namely that the sum of these two weight factors is always 1. This reminds, of course, of the simple mixture assumption. And they introduced the difference of these two quantities to be the order parameter phi. And with an approach like that, one has some nice consequences. So the first consequence is that the velocity field is indeed divergence free. So this is a simple computation. Just take the formula, insert the definition for phi I, use that this is constant, then take the continuity equation for each individual species and use the volume incompressibility to get the 0. The second consequence is if we have these conditions at hand, then of course also the individual masses depend linearly on the order parameter, and assuming already now, and it will turn out to be true, that this order parameter is conserved, I mean the integral of this order parameter is conserved, then of course also individual masses are conserved. Nevertheless, this model has a slight drawback, namely it's apparently not consistent with thermodynamics. At least all attempts to prove an energy estimate failed so far. Okay, so the desired features of our new models are some features which are already satisfied by the model by Dingsfeld and Schuh, so the solenoidality and also the conservation of individual masses. But in addition, we wanted to be consistent with thermodynamics, so to satisfy an energy estimate. Okay, so let me briefly sketch our modeling. So we start with the balance equations for the total mass, at first for the individual masses, so this is just a continuity equation for each mass. Then if we want to replace the VI by this gross velocity, then of course we have to do a certain correction, and this correction term is called Ji. And if we sum up these equations for I equals 1, I equals 2, then we get a continuity equation for the mass rho, for the mass density rho. Which consequences does this have on the momentum balance? So if we look at this equation as a continuity equation, then it seems that the mass rho is transported by the virtual velocity, so this gross velocity plus a correction term, which comes from this rho minus 1 times J1 plus J2, which comes just from this quantity here. And so the question is, which consequences does this have on the momentum balance? So should we now take V tot multiplied by rho to be the new momentum, or can we also handle everything with the old momentum, just rho times V, or are some mixtures necessary? And in the end, it turns out that a certain kind of mixture leads to a satisfactory result. Namely, we take as a momentum still the old momentum, the cross momentum, so just rho times V, but we transport it not by the velocity V, but by this new velocity, and that way we get a mass momentum system which at least has been proven to be Galilei invariant already a few years ago by Willy Alt. Yeah? And so taking this equation and taking that equation here, we have evolution equations for rho and for the momentum, and what remains is to determine this sum J1 plus J2, which we'll call J, and to determine the coupling force in the Navier-Stokes equation. And that can be done, as it's often the case, for instance, by Onsager's variational principle. In our paper, we also used two different methods, Lagrange multiplier method, microstresses by Gerting. The result was always the same. And before giving this result, I should just mention the physical energy which we used. So it's just the kinetic energy, and then this energy here, that's a Ginzburg-Landau energy, delta positive parameter, which is supposed to be small, even to 10 to 0, since delta gives the width of the diffuse interface, and F is just the double well potential. Yeah? And if we do this, then we come up in the end with this system. So you have the new momentum equation, which looks pretty much the same as the old momentum equation, or as the Navier-Stokes equation, with the only exception that there is here this new convective coupling of the flux of the Cahn-Hilliard equation with the momentum equation, and as a dependency of the mass density on the order parameter phi, we just get this linear relationship which you see here. Okay. Now, having obtained this result, let us summarize what we did so far and which questions we should answer next. So, of course, we have found this model, and since it was derived by Onsager's relational principle, it's more or less clear that it will satisfy an energy estimate in the way we want it to have. But it seems not to be reasonable to invest time on modeling if it's not possible also to formulate a numerical scheme which has the same properties. And therefore the first question now is how to formulate such a scheme which also satisfies the energy estimate. And having done this, in particular having a scheme which has this structure, then it should be possible to prove the convergence of discrete solutions. And finally, as I mentioned before, the physical importance of this blue-colored term. And it will turn out in the end that that really the connection of this term to the energy, in particular to the surface energy, will give us an idea how to find a setting where this term really becomes important. Okay, so let me continue with the formulation of a discrete scheme. And to motivate this formulation, let me first show you how we get the energy estimate in the continuous setting. So here, the Navier-Stokes equation, I mean this new momentum equation in a weak formulation, and then the Cahn-Hilliard equation in a weak formulation. And the energy estimate in the continuous setting is easily derived. So one has to choose W as V in this form. Then one gets this relation which is written down here. Then for the Cahn-Hilliard equation one has to do the usual stuff, which means test this equation by mu, so choosing theta as mu, and then multiplying this equation, or a weak formulation of this equation, by the time derivative of phi. This gives the relation which you see here. And then finally, and that's the crucial part, finally one has to test again the Cahn-Hilliard equation here by a multiple of the square of the velocity field. And this multiple is just the derivative of rho with respect to phi. And so if you compare colors, then you see that the two red terms cancel out each other, the two green terms cancel out each other, that term cancels out against that term, the two blue terms add up to be the time derivative of the kinetic energy, and these two terms add up to be the time derivative of the surface energy. For simplicity, I now just set delta equals 1, yeah? So there's no delta visible anymore. And the two remaining terms, that one is just viscous dissipation, and this is the other dissipative term. Okay, now in the continuous setting, problematic is this term here. So we cannot use squares of a velocity field as test functions in a finite element formulation for a scalar equation. Therefore, one would be forced to take here some kind of orthogonal projection, but this means that this orthogonal projection also appears here, and then we have to take those orthogonal projections also in that equation over there, and then it becomes a mess. But there is a way out, and it's just the result of the consequence of the following idea. Why not reformulating the momentum equation in such a way that it is sufficient to test this new momentum equation by the velocity field, and then the Cahn-Hilliard equation by mu, and this equation by phi t, which of course is allowed, and in such a way immediately get the the energy estimate. And that's possible. To achieve this, we have here a very useful identity, and which is obtained by testing the Canhilliard equation in an appropriate way. And let's have a look at these red terms here. So if I add those two terms, then I get here a factor 1/2, and so I realize there's skew symmetry around with that term. So if I take v then as testing function, so these three terms cancel out each other, and the same also happens with these three terms if I take v as testing function for w. So these terms are vanished, and also the red and the green term in this equation is vanished. At least when v has been when w has been chosen to be v, and the only remaining terms are these terms here. So they look quite identical. So that's not a sign of dyscalculia. It is by purpose. So this term together with that term just gives the time derivative of rho times v, and well, this term is just an leftover which we have to keep. Okay. And so we add this equation to that equation, and then we are able to formulate our scheme. And for a moment, please forget everything which is red and everything which is blue on this transparency, and then you see that it is exactly the scheme which we or the formulation which we get by taking the sum. So here we have the two time derivative terms, then here we have the skew symmetric terms which contain the v, and here we have the skew symmetric terms which contain the flux, and this is the dissipative, the viscous dissipative term, and that's the force term on the right hand side. Okay, and of course we also can put weak formulations, discrete weak formulations for phi and for mu, and we of course also should put time indices here, and also take discrete spaces, finite element spaces. So UH, that's linear finite element. Here the discretely divergence-free elements, so in a Taylor-Hood setting, for instance. And this subscript H here denotes the so-called Lambert masses scalar product. And there is something more, namely the strange F plus and F minus. F plus is just the convex part of the double well potential, and F minus is the concave part of the double well potential, and it's reasonable to discretize them differently. The stabilizing term implicitly, the destabilizing term explicitly, to get nice estimates. Yeah, using just the convexity or concavity. Okay. Now let us address some difficulties which come with this formulation. So the first difficulty is the following one. The Canhilliard equation is fourth order, so there's no maximum principle around. So at first you do not have any control of phi. So phi might become very negative. Yeah, but this means, since we have here this linear relationship, that also our rho of phi may become negative, which would be bad for the energy estimate, since it enters the kinetic energy. Yeah, and therefore we somehow have to guarantee positivity of, well, I call it now rho tau h, tau time increment, h spatial increment, to denote the discrete solutions. Yeah. And in the continuous setting, one would take either logarithmic potentials, singular potentials, to bound it to an interval -1 plus epsilon to 1 minus epsilon, or one would take degenerate mobilities in the Canhilliard equation to confine the phase field to -1, 1. But in the discrete setting, of course, a certain regularization is needed, since we cannot deal with degenerate terms, nor can we deal with singular terms. But integral estimates, of course, deteriorate when external forces are present. So this means that in principle, for each external force, we are forced to take another discretization to have the same bound. And for this reason we proceed differently. We just regularize this rho of phi by some kind of cut off, such that it is stays positive. We choose a constant mobility, and we take a double well potential which has polynomial growth with the parameter p as it is indicated here. And in fact, looking at the papers on numerical analysis for this equation in the equal density case, one always sees the same. Also constant mobility, and also the double well potential just with growth p equals 2 for 4, so just a generic version. Okay, so yes, equal density case, Xiaobing-Feng, or K. Welford and Vanessa Stiles, and now the non-equal density case. Let me, so don't be afraid, I will not get into the proof, it's quite technical, but nevertheless, I would like to address at least two difficulties. So the first difficulty is compactness with respect to time in the momentum equation. So usually mathematicians are happy when they can control certain spatial derivatives of a solution, and when they also can somehow control the time difference quotient of the solution. But since rho and phi are already settled by the Canhilliard equation, so we should get here some compactness with respect to time for the velocity field. And if we have this, then we are able to show that there is a strong converging subsequence at least. But here we are in a bad situation. So we have this product rho times v. So this product rho times v is certainly not contained in the space of discretely divergence-free velocity field, since this rho works as a weight, and therefore the approach which one would use in the equal density case, namely just taking an arbitrary test function, taking then the orthogonal projection onto the space of discretely divergence-free elements, and from that getting an estimate of d tau v. This does not work. Okay, and the next difficulty is just a passage to the limit tau h tending to 0. Just look at this term here. So there is a flux j of the Canhilliard equation, and there is a gradient of the velocity field. Both are only bounded in L2 of space-time, so the product is only bounded in L1 of space-time, and so it's not clear whether this product will converge to a function. It also can become a measure, and moreover, it's not clear even when it converges to a function, that this function will be given as a product of gradient v times gradient mu. Yeah? And but on the other hand, gradient v is a gradient, and it might be nice to control somehow the divergence of j, and then but of course we cannot do this in the usual continuous setting, since mu is just piecewise linear, so gradient mu is piecewise constant, so we have to take the divergence of something which is piecewise constant. Yeah, So we need some a strange version of compensated compactness. Okay, and the key to solve all these problems is in fact to prove much higher regularity for the phase field and for the chemical potential, and this is the heart of the paper in fact, but nevertheless I will just give the results. So one can show that this time difference quotient is an L2 of space-time, that the discrete Laplacian of the phase field is in L infinity L2, and that the discrete Laplacian of the chemical potential is in L2 of space-time. And note that this discrete Laplacian of mu is translated to the continuous setting as something like a fourth-order derivative of phi. So some generalized fourth-order derivative of these piecewise linear functions. Okay, and then it's quite easy to get higher regularity for J just by using the nice bounds on Laplacian of mu tau h. One gets that J is bound in L2, L6, and in L4, L2, at least in 3 spatial dimension. In 2 it's even better. And then one can interpolate a little bit and show, in fact, that this converges to that as wanted, and in a LP LR space with P and R larger than 1. Okay. Now the second, well, it was the first difficulty. So compactness with respect to time. So using the high regularity of d tau phi, which of course due to the relationship translates to a similar property of d tau rho, then it's possible to prove compactness in time for the orthogonal L2 projection of this product rho times v. So this orthogonal L2 projection strongly converges, and it only remains to do the identification, and here's a quite nice result on this. So we assume the following, that the discrete solutions are weakly convergent in L infinity L2 and in L2 H1. Then this orthogonal projection should strongly converge toward a certain function z in L2 of omega t, and also the phi or the rho should strongly converge in L2 of space-time, and then it's possible to deduce that V is divergence-free, and that this set is in fact the Helmholtz projection of rho times V, and that also the product rho V squared converges to its corresponding function in the continuous setting, so that the kinetic energies converge. Yeah, and I will just prove the last item because it's the most funniest result. So we have this result using that V tau h is discretely divergence-free. We can smuggle in here the orthogonal projection. Then we know that this term strongly converges to z, but from this item we know that z is equal to the Helmholtz projection of rho v, so it converges to that term. V tau h converges weakly to v, so the whole term converges to that term, and we use again the orthogonality properties of the Helmholtz projection to get this result. And from this, of course, we also can deduce that that V tau h strongly converges in L2 to V. Okay, and then putting everything together, we get an existence result in 2 and 3 space dimensions. We have to satisfy certain structural conditions on projection operators, which are okay for instance, P2, P0, and Taylor-Hood elements. And we need sufficiently regular initial data, and then a subsequence converts to a generalized weak solution. So the question is, what a generalized solution is, A generalized solution is a solution which still carries this row regularization with itself. Yeah, and for this reason, it's not possible to get rid of these skew symmetric terms which we have here, unless we can confine phi to the regime where rho of phi is linear, because then we can do the reformulation back. And interestingly, to do this, we just need that phi stays bounded in an interval which is related to the so-called Atwood number. The Atwood number is a number used by engineers to measure the deviation or the discrepancy of the two mass densities. So it's just a ratio rho 2 minus rho 1 over the sum. So it's 0 for identical masses, and it's 1 if the ratio is infinity. Okay, and so we see that that if phi stays bounded in this interval here, Atwood number to the minus 1, negative as a left boundary, Atwood to the minus 1, positive as a right boundary, then phi is a weak solution, and the weak solution looks already much better. So we just have the formulation which we would expect from Navier-Stokes equation, and so existence of weak solutions is now depending on optimal bounds on the L infinity norm of the phase field. So we can always be sure that there is a positive time for which a generalized solution is a weak solution, but it just depends on this condition, which is of course a problem of L infinity bounds for phi, whether this solution stays to be a weak solution. Okay, so this was convergence. Let me now come to simulations and model comparison. So the scheme has been implemented in 2D, and implementation in 3D also started. As a working horse, we use stabilized P1 elements, and for the precise computations we take Taylor-Hood elements. And so now I should go here, and so here's just the first 3D rising droplet. I have to apologize for this bad quality here, but there is a problem with the computer, with this movie, and the scheme itself is adaptive with respect to space and to time, and the time increment is related to the propagation speed of the interface. This scheme, this model, participated already at a benchmark computation, namely on Taylor flow of a pressure-driven bubble in a narrow channel. And this is a paper written by, I think, 5 groups, so 2 coming from sharp interface models, 2 coming from diffuse interface model, and 1 coming from experimental physics to provide the data. And diffuse interface models, of course, face a conceptual difficulty, namely there may occur a certain sticking phenomenon if the distance between the bubble and the wall and the thickness of the diffuse interface, of course, are of the same magnitude, then the bubble just stays where it is and deforms in a very unpleasant way. But one quite nice approach to get out of this problem is also to take liquid-solid interfacial energies into account, which may model, of course, each contact angle, but taking contact angles slightly larger than 90 degrees is already sufficient, and this entails in the model as a second boundary condition in the Canhilliard equation, just a non-standard equation as you see here. So it's no longer normal derivative of phi equals 0, but it's equal to this derivative here, and this function sigma ls is to interpolate between the interfacial energies liquid-solid, between solid and liquid 1 and solid and liquid 2, yeah, depending on phi. And the outcome is that we found a nice agreement with sharp interface computation and physical experiments. So here you see the different codes. So I think econtrop, that's us, and these first two, these are sharp interface computations, but sharp interface computations which did not take the bubble itself into account, but only the surrounding liquid. But there is some result which is not so extremely nice, namely the computation based just on the model by Ding, Spelt and Chu performs similarly well. Yeah. So one could get the impression that that I just wasted your time now by introducing this new term and by proving convergence and everything. So therefore we have to address the question whether we can find settings where this term really has an effect. And so the first attempt is to look at rising droplets with a stronger discrepancy. So here is Ding-Spelt-Chu, here is Abel-Skarke-Grün, and wait a second. Yes, and so at first it looks pretty much the same, but then when the topological change appears, then some differences are clearly visible. But this was just a quick and dirty computation, and that is not what I really want to present you. The question is whether, since we spoke so much about stability and so on, the question is whether the DSS model may become unstable. And this is of course now a dangerous field, since we only made our computations. Of course, it's not so complicated if one has an algorithm for the entire problem, just to cancel this term and do a computation based on Ding-Spelt. And so it may nevertheless be that the results which I'm going to present you now are not correct, since they have not been tested by a third person, but nevertheless they are probably quite convincing. So, oh no, I made a mistake, sorry. So let us have again a look at this term here. So what was J? J is the flux of the Canhilliard equation. So it is proportional to the gradient of mu. And mu, so the chemical potential, and the chemical potential is the first variation of the liquid-liquid surface energy. Yeah, and this liquid-liquid surface energy, so the diffuse interface energy, is the diffuse interface approximation of the surface area, and the first variation of the surface area is the mean curvature. So from this point of view, mu is an approximation of the mean curvature of the interface, and so J as gradient, mu is something like a curvature gradient. And so from this point of view, one should look for a situation where one gets a self-propelling curvature singularity, or at least something with a strong curvature variation. And so the setting is the following. We take a droplet surrounded by an ambient liquid, which is heavier, so it should still be a rising droplet. But, and that's important, the ambient liquid is less viscous than the droplet. And in this situation, it happens what you see here. We have this tip formation, and this tip formation, in fact, is a self-propelling, well, probably not singularity, but at least something which induces strong changes in the curvature. And then doing experiments with Dingsbelt and Schuh, and with our model, something surprising occurred. Namely, if the Atwood number is sufficiently large, so if the discrepancy between the masses is sufficiently large, then the phase field blows up for the DSS computations, whereas the phase field for AGG remains still in this interval, which we have identified before to be the regime where we have a weak solution. So it was just this interval, in principle, Atwood number to the -1 to Atwood number to the -1. So here negative, they're positive, and the consequence is that the linear solvers do not converge anymore, and so the computations here had to be stopped. So yes, and in fact, these purple-red patches here, these are the regions where the phase field for Dingsbelt-Schuh became unstable. And these strange lines here, which do not look so extremely symmetric, they have this form due to the asymmetries of the underlying grid. Yeah? Okay, and now I'm forced to conclude, but I really want to conclude. So I've shown you the first convergence result for the numerical scheme for two phase flow with different mass densities, and we see that that we should get better bounds for the phase field of generalized solutions to make sure that our generalized solutions are weak solutions globally in time. And other perspectives extend the approach to species transport, surfactants, electrowetting, and it may also be possible to take effects on the micro scale into account. And here I have listed a few papers which were written in this context. So in particular also an independent existence result on the model by the colleagues from Regensburg. And now I thank you for your attention.
Next questions?
I have a very simple question. So I did not understand the definition of rho tilde. You said this would be the mass density these phases would take if they were alone. But
yes, so in this model, the problem is to get values of rho at each space-time point x and t, yeah, and this rho, of course, is a sum of the actual density of species 1 and species 2. Okay, and in each volume element, so there are since this is a mixture, and this of course applies first to the diffuse interface, not to the pure phases. Since it is a mixture, the mass in each volume element might not be as large as it would be if there were not the other component present. And so from this point of view, we just take these phi I as the quotient of rho I at xt, so it should be also a phi I of xt over rho I tilde, and rho I tilde, that would be the mass which is attained when there is just a species 1 in this volume element. So in principle, rho I tilde is equal to rho I of, yes, either 1 or minus 1. It depends on the I.
It's just a reference density.
Yeah.
More questions? Well, I have a question. Your model should produce somehow Marangoni flow. Where can you identify where it comes from? Where it can come from?
Marangoni flow. So you mean due to the fact that
with some changes of density along this diffuse interface.
Yes, but that is presently not included. So
if you can have a look at your equations, maybe you can have a look
yes,
at the
but
slide with your equation.
yeah, okay. So let us look at the.
Well, it does not
First,
appear.
no,
It
yes.
does not appear explicitly, but I believe it should be hidden
No,
somewhere.
it should not be given because the surface tension in this model. No, this was too far. Let's have a look at the energy here. Well, what is missing? That is the surface tension term. So there should be a factor sigma in front of the Ginzburg-Lambda energy.
No,
and at the moment we just take sigma equals 1, so there's no Marangoni. But if we strive for Marangoni effects, then we should take also this sigma of phi to be dependent on this sigma, this is surface tension coefficient, to be dependent on phi. But that is something which is not included at this stage yet.
So thank you.